Weiss hooked 192 rats by their tails to a live electric wire. He gave some of the rodents a control switch, but left the others to simply grin and bear it. The unsuspecting rodents would at first scurry and jump to find a quick way out. The luckier of the beasts would soon discover their control buttons. When the current sizzled their sterns, they would lunge for the switch and turn it off, rescuing both themselves and their switchless fellow sufferers. The rats whose frantic searches resulted in no discovery of a means of control, on the other hand, would eventually give up their struggle, lie down on the cage floor, and accept their jolts with an air of resignation. Even worse, the rats without the control levers would end up physical wrecks, scrawny, unkempt, and ulcerated, while those who could slam the current off stayed reasonably plump and fit. All this despite the fact that each and every rat received exactly the same surge of current for the same amount of time and at the same instant. As learned helplessness experiments continued, it was discovered that more than mere laziness crippled the beasts who couldn't find a way to abort their punishment. Their immune systems no longer protected them from disease. If given a way to escape their situation, their perceptions were too bleary to notice something as simple as an open doorway out. Their self-destruct mechanisms had taken control. All indications were that these self-maiming reflexes were physiologically pre-programmed. Most telling was the fact that the experimental animals able to cope with the slings and arrows of a researcher's outrageous fortunes retained a vigorous immune system, a relatively keen perception of the world around them, and remained energetic, despite the periodic spurts of abuse. The rats without control switches had been sabotaged by their own bodies, poisoned by their own stress hormones. How could this internally inflicted damage aid the victims in projecting their precious genes into the next generation? A naturalist named V.C. Wynne Edwards, however, had already observed the effects of these phenomenon au naturel. Most species in the wild are not isolated by a cage, but live as part of a herd, a flock, a colony, or a pack. Edwards studied communities of wild grouse in the Scottish moors. Here, punishments and rewards were handed out not by scientists, but by wind, rain, other grouse, and by poultry-loving prowlers of all kinds. Male grouse who mastered their surroundings and were socially adept managed to corner the best food and the largest plots of real estate. In the process, they became strong and self-confident. Those less able to forage successfully or to grab a large plot of land became droopy, dispirited, and unkempt. Weakened, they entered the seasonal competition for females, attempting to outdo their problem-mastering flockmates in tournaments of ferocity and of fancy display. Each morning they erected the combs on their heads in a feeble manner which showed their lack of confidence, fluttered in the air with as much flash as they could muster, battled for control of land, and usually lost. Their failure to find a way to dominate their natural environment led to a corresponding failure to gain control in their social milieu. By winter's end, almost all of the losing red grouse were dead. Victims, says Wynne Edwards, of the after-effects of social exclusion. The triumphant birds, on the other hand, were rewarded with avian harems and patches of land not only rich in food, but heavily fortified by high heather plants against passing predators. Wynne Edwards theorized that he was watching group selection at work. The birds whose failure had led to a physical decline, he reasoned, were unwittingly sacrificing themselves to adjust the group size to the carrying capacity, the amount of food and other necessities in their locale. The Scot announced his conclusions in 1962. By 1964, William Hamilton's equations had taken the evolutionary community by storm. Wynne Edwards became the poster boy for group selection and was driven from scientific respectability. What Wynne Edwards had seen at work was a complex adaptive system devilishly similar to a neural net. Those individuals within the group capable of finding solutions to the problems of the moment were rewarded with dominance, desirable food, luxury lodging, and sexual privileges. The weak links in the group's neural net, the individuals who had not found a means of solving the puzzles thrown their way, were isolated and impoverished by the social system and disabled internally. In other words, a flock of feathered aviators had shown all the characteristics of a collective learning machine. Later, Israeli naturalist Amatz Zahavi would postulate that bird roosts function as communal information processing centers. More about this later when we make friends with the raven. Now try a little twist of thought. If you put Zahavi's conjecture together with the observations of Wynne Edwards, add in the evidence from learned helplessness experiments, and toss in the discoveries of complex adaptive systems researchers, an interesting pattern emerges. My work since 1981 has been to put that jigsaw puzzle together. Here's how the picture looks once the various parts are snapped in place. Social animals are linked in networks of information exchange. Meanwhile, self-destruct mechanisms turn a creature on and off depending on his or her ability to get a handle on the tricks and traps of circumstance. The result is a complex adaptive system, a web of semi-independent operatives linked to form a learning machine. How effective is this collective learning mesh? As David Sloan Wilson discovered, a group usually solves problems better than the individuals within it. Pit one socially networked problem-solving web against another, a constant occurrence in nature, and the one which most successfully takes advantage of complex adaptive system rules, that which is the most powerful cooperative learning contraption, will almost always win.